So in genomics data, we usually have many predictors. Gene expression for thousands of genes, that could be our predictor. SNPs for thousands of SNPs, those could be our predictors, etc. The outcome is usually binary, although not always. But a very common one is good prognosis versus not good prognosis. Or you could have something like disease or not disease. So how do we do this? We're going to use a simple illustration using two variables. So you can think of this as just two genes. However, going forward, we're going to expand this list to many genes. But let's start with two. In the previous module, we did one, father's height, to predict son's height. Now we have two variables. So what we're after is the conditional expectation of y given x1 and x2. So for any pair of x's, we want to find the average value of all the y's with those two values. Now, because this is a 0-1 case, we have y is either a 0 or a 1, say a case or a control. This expectation is equivalent to the probability of seeing a 1 given x and 1. So I have generated simulated data. And in this plot here, I am showing you this probability as a function of x1 and x2. So you have x1 and x2 on the two axes. In blue, I'm showing you places where that probability is bigger than a half. And in orange, I'm showing you places where that probability is less than a half. So anything in this region we would probably call a 0, and anything in this region we would call a 1. So we don't actually know this. This is where the data is going to be generated from. It's the hidden truth. We don't know it. All we get to see is data like this. So here we have some data where we have x1, x2. You can think of them as gene expression for one gene and a second gene. And we have outcomes shown with color. So if you're a 0, you're orange. If you're a 1, you're purple. And now the question is, for any new x, for any new x1, x2, can we give a prediction? And how good would this prediction be? So to help answer that question, I have kept, and this is a very standard trick in machine learning problems, I have kept to the side what is called a test set, which I will not use to generate my prediction models. I'm going to build prediction models on a training set, and then I'm going to check how well they work on a test set. The test set is not used to create the prediction models. So let's start simple. Let's try linear regression again, just because we know how to do it. So the linear regression model would model the expectation of y given x, here x is two-dimensional, with just a linear combination of the x's. We estimate it with least squares, and we get the beta hats. And now we have a prediction formula. So any x, any x1, x2, I just stick them in here, and I'll get a prediction. F of x will be any number, but if it's bigger than a half, I'll predict a 1. If it's smaller than a half, I'll predict a 0. So if I do that with this data, this is what I get. This is the map that I get. The points are the data. This line is the place where on the one side, x1s, x2 are going to be bigger than a half. x1s and x2s below that line are going to predict something smaller than a half. So this is the line where that linear formula is equal to a half. So anything above it is bigger than a half. Anything below it is smaller than a half. So you can see that we would make several errors. Anytime you see an orange point in the purple area, that's a mistake, and vice versa. So here we make 29.5% mistakes. Now this is the training data. How well do we do on the test data? Just a little bit worse, and that's somewhat expected because this is not a very flexible model. Now, why do we use linear regression here? There was really no reason to believe that the shape of E of y given x is of this form. There was no reason to believe it was a linear function of x and 1 and x2. In the next module, we're going to introduce one of the many approaches to estimating these conditional expectations that are not based on linear models.